How's it going, everybody? Today we're working on a little bit of circuit theory. Specifically, we're talking second order circuits. Okay, some of you may know them as RLC circuits, but whatever. It's all second order. Okay, this is our example. So we've got a voltage source in series with a 8 kilo ohm resistor, a 160 millihenry inductor, and a 10 nanofarad capacitor. That is 10 N there, guys. All right. The voltage on that capacitor is VC. Some people call it the output. I'm just going to call it the voltage on the capacitor, VC. Okay. So they tell us at time t equals 0, the voltage source's value jumps from 50 to 250. Now that's going to happen, of course, instantaneously. All right. Well, I shouldn't say of course, but the idea is it happens instantaneously. With all of that being said, find VC as a function of time. Okay. So the moment I see that I'm dealing with a second order circuit, I got a capacitor and an inductor. Here's my step one. First thing I do is just find my W naught squared, which is equal to 1 over LC. L is going to be 160. C is going to be 10. 160 is going to be times 10 to the negative 3 for the milli. And then I got 10 to the negative 9 for the micro. Solve for my W squared, W squared ends up being 625 times 10 to the 6. And that'll be radians per second. Actually, it'll be radians squared per second squared, excuse me. Okay, so that is my W squared. Okay, cool. So that's kind of done. Now from here, I just put up my little brackets. Remember, I'm just kind of going in the order. I'm not really thinking about it anymore. This is my step 2. My step 2, I'm going to solve it as if it were a first order circuit. So I'll put up my 4 little boxes. Okay, sometimes this is going to be easier. Sometimes it's going to be a little bit harder, but it's all good. So in my 4 brackets, my top leftmost bracket, excuse me, I'm going to draw the circuit before the switch. In this case, there is no switch, but there is a change in the source. So the change in the source will function as our switch. So beforehand, I have 50 volts here. I got my resistor. Now remember, the inductor stabilizes because it's just before. Stabilizes into a short. The capacitor stabilizes into an open, but it does have its voltage. So I'll say, I'm just going to call it VC minus. That is equal to VC plus. And in this case, it actually will be 50 volts. Okay. How do I know that? Because remember, if I were to look at between the nodes of the capacitor, there is no current. If there is no current, that means, and this is all in series, that means that nothing in this thing has, the current is 0 basically everywhere. All right, if the current is 0 everywhere, then that means the current on this resistor right here is 0. If the current on the resistor is 0, that means it is receiving 0 volts, which means nothing. The resistor doesn't really exist, is what I'm trying to tell you guys. So basically that's what we have. Therefore, the voltage on that capacitor will be 50 volts. Okay. Do the same thing with the infinity. It actually ends up giving you the same type of answer. I'm going to change my voltage source to 250 because that's what they tell me happens. The inductor will still short out, the capacitor will still open up, and because of the same exact reason from before, my V at infinity is going to equal 250 volts. Okay? So, great. I got my initial and my final states found. Cool. Now I go to my alpha. Alright, in this case, there is only one resistor, so I don't have to worry about devolving, I don't have to worry about doing the Thevenin. If there's just one resistor, there can only be one R. Alright, I don't have to worry about finding my R equivalent. So all I have to do is note that they are in series, the inductor and the capacitor. Since they are in series, alpha is equal to, it's going to run on the 1 over tau for the inductor, which would be R over 2L, which would be 8K over 2 times by 160 times by 10 to the negative 3. Alpha is going to end up being, what does alpha end up being? Hold on. Actually, you know what? I'd actually gone and calculated alpha squared. So that is going to give you some number. Sorry about that. That's going to give you some number. All right. I actually went and calculated alpha squared automatically because I knew it was of paramount importance to me. So alpha squared actually ends up being the same thing. Oh, found alpha. Great. Alpha. Great. All right. Here we go. Alpha ends up being 25,000 radians per second. Okay, cool. So I found my alpha. All right, and I'll put alpha squared at the bottom since I just ran out of some space here. All right. So from here, I'm on my 0 plus circuit. Remind you, the whole purpose of this problem is to find my VC term. So when I'm on my 0 plus circuit, I'm actually going to be focusing on my VC. So I draw the circuit just after the switch, which maintains a 250 volts, but now everything is on. So I've got my inductor and I've got my capacitor. Okay, and this I think is one of the trickier parts in solving this bad boy. You still have to use everything you know. All right, so what happens is the current on this inductor is actually equal to 0 because I minus on the inductor is the same thing as I plus, and I here was 0. We solve for that. Therefore, because it's 0, this inductor actually dies away again. Poor baby. And it ends up, instead of becoming a short, it's 0 current now, so I can represent it as an open. Because it is open, I know that there is no current anywhere else in this circuit. Okay. Taking a look at this voltage on the capacitor, that is going to be equal to 50. Okay, and that's going to be my V plus. So I can then say IC at 0 plus is also 0. Great. Now the last thing you'll be needing to look for, since I'm going on the VC term, I'm going to be needing my derivative of the voltage on the capacitor at 0 plus. So I guess I'll put the 0 plus, really put the 0 there. At 0 plus, and that I have to actually solve for. Okay, well the change in the voltage on the capacitor is equal to the current. If I divided, this is on the capacitor, excuse me, if I divide it by the capacitance, this actually is the derivative of the voltage on the capacitor. It's just the, and this is actually going to be a part, this part right here that I'm circling in blue, that's actually going to be the part that a lot of people forget how to do, all right? And I'm doing a little bit early, and you're going to see why I definitely need it, you know, in probably in a minute or so. But that's going to end up being IC over C. Well, I just proved that IC was equal to 0, and I got that from my understanding of IL. Okay, remember, it's very, very common that the inductor, or I'm sorry, if you're looking for the voltage on the capacitor, you'll end up needing the current on the inductor. If you're looking for maybe the current on an inductor, you'll end up needing the voltage on the capacitor. Because of this 0 plus step, they're very intricately related, all right? So the inductor's current actually ended up proving, proving the existence of the derivative of the capacitor's voltage, and that's what you will 100% need to do when you're doing these problems, all right? That step cannot be missed because you will need it later, okay? So now that I've done that, my step 2 has been completed. I can go to my step 3 now. Step 3 is in comparing my alpha squared to my omega squared. Alpha squared actually ends up being 625 times 10 to the 6, which is equal to omega squared, and because of that I am dealing with a critically damped, I'm just going to put crit damp. Okay, so I now identify that I'm dealing with a critically damped situation, and I just have to remember the critically damped situation formula. So if I'm looking for the voltage, it'll be the voltage on the capacitor as a function of time. That'll be V final or V infinity, whatever you want to call it. In this case I used infinity, so I'll just call it VC infinity. That'll be a plus. In the critically damped situation uses time, A1 times T plus A2. And I know earlier I might have used D or B. It doesn't really matter what you call it as long as you know it's a constant. And that'll be to e to the negative alpha times time. Okay, because of the critically damped situation, it runs on the Neper frequency, the damping frequency, instead of the S terms. Okay, so great. I know my alpha. I found it earlier. I found my V at infinity. Okay, all I have to do now is find A1 and A2. So what I will do is I'll put it over here. To find my A1, I'll write out this equation. Again, the only thing is I'm going to use the 0 plus. Remember, this is finding A1 and A2 are all about the initial conditions. So I use VC 0 plus, which I solved and I know is actually equal to 50. And that has to equal A1 times T. I'm sorry, VC infinity, which is 250. Okay, just remember that that's 250. Plus A1 times T. So that's A1 times by 0 plus, which is 0, plus A2 times by e to the negative 0, all right, because T ends up being 0. So this gives me a statement of 50 equals 250, and what happens is e to the 0 is actually equal to 1. The A1 dies away, so I get plus A2, and I can solve for A2. A2 ends up being negative 200. Great. So with that, I have found my A1. Now, to come to my A2, and this is when you need your derivative. I take the derivative of my parent function, if you will. When I take the derivative, I'm going to get dvc dt. But now I'm going to plug in, with the derivative, I'm going to evaluate that derivative at 0 plus again. Well, I found earlier that dvc dt is actually equal to 0. And you do that. You say this is equal to 0, and that's perfectly fine. It actually ends up happening quite often. But when I took my derivative of all of this jazz, I'm going to end up with a chain rule. Okay, and for this time, once I'll do it all out. But later on, I won't really be doing it out so often because I'm expecting that you will have practiced it to the point where it's kind of just burned into your head. So I'll have a1 times t plus a2. And I know my t's look like plus signs, and that's kind of wonky. I'll have to work on that. And this is going to give me the derivative, so I'll now have to, so that's the inside term, and I have to take the derivative of the outside term. That's going to be this. And I have to add to that, because it's a chain rule, the derivative of the inside term. So now I'm going to have a1. The derivative of a2 is 0, and then I can multiply by e to the negative alpha t. Okay. So now I'm going to plug in t equals, and I guess I'll do it in red. T equals 0 plus, 0 plus, and 0 plus. And what ends up happening is I get, excuse me, 0 equals, the first at dies away. I'm going to end up having negative alpha a2. And I add to it my a1 because my e to the 0 power ends up being 1. Now, I learned or solved earlier for a2. a2 I know is equal to negative 200. So with this, I can actually solve for a1. Okay. When you end up solving for a1, you're gonna get 5 times 10 to the 6. Okay, and I know it's weird to have negative 200 then 5 times 10 to the 6, but if you're doing everything properly, if you set up everything properly based on your concepts and, you know, all the stuff that you've learned, then the math is just gonna tell you what happens. All right. So now that I've ended up solving for everything, I can actually give a final statement. Come on to the left side of the thing again. Vc as a function of t is going to be 250. Actually, you know what? I'll bring it down even more because I'm going to need to stretch this some. Vc as a function of time is going to be 250. That's my final value. Plus a1, which was negative 5 times 10 to the 6. That's going to be multiplied by t. Plus a2, which was a negative value. So this t minus 200, which is my a2. E to the negative alpha, which is, I think alpha was what, 25,000? Yep, 25,000. 25,000 t. And this, actually, yeah. This is my answer. Okay. And that's how you do it, guys. Just a really nice run through, nice solid problem, nice opening statement problem for us to get into the feel of how to do these types of problems. I will say where you'll find the most difficulty is in your 0 plus analysis, and especially inside of your 0 plus analysis, doing this derivative analysis. That's really where people get stuck. Then derivative analysis here, and also in finding your second equation that's necessary. I don't recommend that you try to rote memorize what the equations end up becoming. I just actually, in this case, when it comes down to solving for a1 and a2, the constants involved for your function, I just recommend you remember that it comes from the initial conditions. One is going to be the contemporary, or the standard one, and the other one will come from the derivative. So the derivative step, those will be the two issues that typically give students the most angst. There are going to be some situations where finding your alpha sucks, but practice makes perfect. If you know what you're doing, if you know how to do your Thevenin, then you'll be able to find alpha even still, even if it's kind of wonky. But all in all, this is how you handle it. This case, we had a critical damp situation, but if alpha squared was less than w squared, I would have handled it with the underdamp. If it was greater, I would have handled it with the overdamp, and my equation would have changed, but I would have still ended up solving my system of equations for my constants, my initial condition constants. So all in all, I hope this helps.